Hello and welcome to the talk Cryptocurrencies with Security Policies and Two-Factor Authentication. Let's dive straight in. Recovery is challenging with cryptocurrencies. The only authentication factor is the private key associated with the wallet. What happens if this key is lost? There's no trusted authority, like in traditional banking, that can recover the funds for you. The loss of a wallet means the loss of the associated funds. Additionally, there have been many attacks carried out against owners of cryptocurrencies. Some of them could have been prevented if the owner had the possibility of requiring a second-factor authentication. These are all issues that traditional banking has had to manage since a couple of decades. The use of a second factor is widely deployed. Security policies in banking, like requiring a second factor for a certain beneficiary or for a certain transaction amount threshold, are there to keep the user safe. All this leads us to our research question. Can we take the lessons learned in the traditional banking domain and apply them fruitfully to blockchain-based systems without compromising their decentralized nature? We will define a distributed zero tester and show that its implementation is efficient for the Ethereum blockchain. We will also show that U2F, a token protocol, can also be implemented efficiently on the blockchain. Before we jump to the contribution, I want to give a quick overview of our design principles. First off is distributed trust. The two-factor authentication must not rely on the existence of a trusted authority. Instead, we propose to leverage a hardware token or distribute the trust among a set of parties. We require the two-factor authentication mechanism to be resilient against benign disconnections and malicious denial-of-service attacks. In distributed environments, communication is typically expensive, as messages have to be broadcasted to all users in the network. For this reason, it is of central importance to minimize the rounds of communication of a two-factor authentication mechanism. Additionally, we aim to build a solution based on well-established cryptographic components, which is efficient enough to be integrated in real-life systems. To give you an overview of the system, the distributed zero tester implementation is shown in detail. We have two smart contracts, a security policy contract and a DZT contract, both running on the Ethereum blockchain. A part of the protocol is also implemented in a client that uses the RPC API of an Ethereum node. The security policies are used as an additional safeguard. A user can select which policy best suits them. Implemented security policies, like a sliding window or flagging transactions to new beneficiaries, can be useful to increase security. The flagging mechanism itself is reasonably cheap to be used in real-life systems. The first scenario is that a user wants to secure their cryptocurrency with a security question. Security questions could be, for example, what's your favorite ice cream flavor, or what's your first car brand? The challenge with those questions is that the answer probably has low entropy. So offline attacks are possible. The standard solution of hashing the answer is also not possible, because everyone could read the answer on the first successful attempt of a user verifying themselves with the answer. We present the distributed zero tester, which solves the challenges around security questions. The protocol is executed by three different types of actors. First, there is the user, which wants to authenticate themselves. Then there is a group of miners that form a committee that validates if the answer to the security question is correct. Finally, there is the smart contract that gives the final verdict and is used to broadcast communication. The DZT has 4 rounds. The first round is setup. The user commits to an answer to the security question, and the miners commit to parts of the secret keys used in the threshold homomorphic encryption. After the setup is finished, the security questions can now be used as a second factor. The next DZT step is query. That means an unauthenticated user attempts to answer the security question. The smart contract broadcasts the answer attempt to all miners. Please note there can be many query rounds. In the response round, the online miners first check if the answer attempt is of correct form. We use non-interactive zero-knowledge proofs for that part. If verified successfully, the answer attempt and the miner secret is used to create part of the final answer. In the verdict round, the smart contract verifies that all answer parts are in correct form, using zero-knowledge proofs again, and sums up the answers. If the summed up answer is correct, the user's transaction can now go through. The DZT fulfills the design goals we set out to use. We instantiate the DZT using a threshold homomorphic encryption scheme and bilinear maps. One note for the implementation is that we use the 256-bit version of Pareto Naring curves, since the Ethereum blockchain has built-in support for this curve. Other curves can be used as well. Since we are using threshold cryptography, at least a certain amount of miners have to be online to verify the security question answer. This graph shows us how the cost of verifying correlates with the committee size, so the online miners. As we can see, the total query cost stays under $1 for a threshold smaller than 14. In another scenario, the user wants to authenticate themselves with a token device. We implement U2F, a challenge response protocol. It has two different phases: registration of the device to the smart contract and verification of a transaction by the device. Each user has to do registration once and verification so long as the security policy contract dictates. In this picture we can see that the standard U2F curve SecP 256R has higher costs than the SecP 256K curve, which is due to inbuilt support in Ethereum. Please note that the U2F standard mandates SecP 256R and cannot be changed. In our solution though, a user can decide on registration which curve they want to use. Thank you for your attention, and if you want to, the code can be found at the URL linked in the slide.